My name is Muhammad Syamilas and my number is DE20127. So I'm going to be proceeding into the introduction. For the project background, the power system is the most massive and complex dynamic system. The power system, like any dynamic system, is constantly susceptible to disturbances and oscillation as it transitions from one operational point to another. The stability analysis of power system is essential for maintaining a steady and secure supply of electricity. Accurately simulating and analyzing the system response becomes essential due to the capacity of the power system increasing as a result of integration of renewable energy sources. So the goal of this project is to create a simulation model in MATLAB to examine the stability of the power system to accurately represent the system behavior, and the model will take into account variables such as the generator characteristic, transmission line parameters, load characteristic, and control system. There has also been an increase in the interconnection of regional power system in order to improve the stability and control condition. But the stability problem has taken a new into dimension. Voltage stability, frequency stability, and inter-area oscillation all have become more of a concern in recent years. So the objective is in this laboratory is to model a test system model of power system using MATLAB Simulink to analyze the dynamic response of the system following a disturbance, and to work in the group to solve the complex power system problem within a limited amount of time. So as number 2 has point out, following the disturbance, which will also be with the variable of different buses. And as for the scope of experiment is to firstly, the transmission system nominal voltage used for this laboratory is 230 kV. The parameter that will be used in this are real power, reactive power, and voltage. And lastly, the load condition used in the system are resistive load, inductive load, and capacitive load. The literature review, as per using MATLAB 4.0, it will be capable of resolving problems in the manner outlined in the majority of commonly available power system analysis, which are nowadays are being integrated. This could be used to conduct load flow analysis, impedance calculation, for calculation, and resistance stability analysis. MATLAB is extensively used by university researchers and students such as myself. And the addition of Simulink to MATLAB, which significantly plays the major role of us into implementing the MATLAB software compared to other software. And for this laboratory activity also, the transition response is a capability that demonstrates the effectiveness of the system response in transitional time unit. Harmonic are disturbance that occur in power distribution system as a consequences of disruption in the current wave and voltages. So that's all for me for the introduction.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Syahira binti Ahmad Safawi. My register number is DE20093. So I will explain about the sudden large increment of load at bus 7. So as we know that bus 7 is at area 1. So for sudden large increment at bus 7, so we will increase the load from 967 megawatts to 1400 megawatts. So this experiment is to show that whether our system is stable or not after the value is increased. So basically, this is the graph that we got from our sudden large increment of load at bus 7. So as we can see that the first factor is the rotor angle versus time, and the WPU is the generator speed versus time, and the APU, PA per unit, is the voltage magnitude versus time, and lastly the VT per unit is the electrical machine power versus time. For the sudden large decrement of load at bus 7, so for this task, the active power from initial value is changed to 483.5 megawatts. From the graph, we can see that the power generation is stopped at 1.390 seconds after decrement, and this is because of the loose synchronized. As we know that PSS is related to the rotor angle stability, which is related to synchronous operation. So it will happen because due to voltage instability.
Okay, Assalamualaikum and hi, my name is Muhammad Zain Mazlan and my metric number is 819070. So now I'm going to explain about the sudden launch increment of load at bus 9 and also the case number 4, which is sudden launch decrement of load at bus 9. So for the first, we need to set the parameter here on the MATLAB. So you can see here. So bus 9 is on, consider is on area 9. So we set up here for the parameters is 50% increment. So we times by 50% and then add the value to this value here that given in this lab sheet. And then after run, we get this result here. For the 50% increment. So from the figure, we can observe that the result of the PSS response with 50% increment of load at bus 9 here. So we observe that this during unstable case. In the yellow marking here, we can observe the sum of parameters like rotor angle, rotor speed, voltage magnitude, and also the electrical machine power. Unstable condition from 0 to 0.6. So there will a sudden load increment at bus 9 for this 1 second here. So what happened become unstable condition. From the blue marking here, we can say that sorry, for the green marking here, we can say that the system is marginally stable from 0.6 for 1 seconds. So all the parameters, like I stated before, with the green marking, we can observe that the system has achieved stability of the parameter waveform, inclusive of the rotor angles, have straightened out. Okay, next is for the sudden launch decrement of load at bus 9. So as you can see, we need to change the parameter here by 50% decrement. So we need to minus by 50% of the actual value. And after that, we get this result here. So from the result we get here, we can observe that during unstable case in the in the orange marking here, we can observe that there are some parameters like rotor angle, rotor speed, the voltage magnitude, and also the electrical machine power in unstable condition from 0 to 2 seconds when there was sudden load decrement at bus 9. So the initial response from 0 to 3 seconds as indicates by the orange box, and after 3 seconds the system starts to stabilize and consider marginally stable here up to 13 seconds, but after 14 seconds the system is stable as indicated in the blue box right here. And I think that's all for me. Thank you.
So following into the number 4.25, case 5, temporary bolted 3-phase fault at bus 8. The figure 4.14 shows the simulation parameters for the temporary 3-phase fault at bus 8, and the fault is set to occur at time. Firstly is the 1 second to 2 seconds for a length of 1 second. As shown, the system becomes unstable at between the period of 1 and 2 seconds due to the temporary fault bus at bus 8. The instability is shown in the red box. The system then tries to stabilize and is considered marginally stable after the fault in the duration between 2 seconds until 8 seconds as indicated by the yellow box. The system is stable from time 0 to for the first second, and from the 8 second until the 20 second as indicated in the green box. So all of this can be referred into the figure 4.14, the condition of the 3-phase fault, and the figure 4.15, the graph of the simulation result. And next, following onto the permanent bolted 3-phase fault at bus 8, from the figure 4.16, it shows the setting parameters of for the experimental. For temporary bolted 3-phase fault at bus 8, the ground choice has to be unticked and set to switching time to first second. It is to exactly know the location for bus 8, the student have to refer to the single line diagram and that's given in the lab sheet. So after we have after we have managed into proceeding with the variables given, we have the result for the figure 4.17, which is the graph of the simulation result. So that's all from me for bus 8. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zul Hazri bin Zakaria, AE 190019. I will explain about the case 7, which is temporary bolt three-phase fault at bus 5. This figure shows the temporary bolt at bus 5, which is between the transformer and bus 5. The fault is made by making a short circuit at the region by tapping each line and ground at a specific time. The fault is created by the value 0.001 ohm at the 14 and 16 second. The time is set by controlling the switching time. So we get the graph for tapping at the 14 second and the 16 second. So at the 14 second, the most stable condition is from 10 until 14 second, and the unstable condition is occurred after the 14 second. So for the graph when set at the 16 second, the most stable condition is from 12 until 16 second, and the unstable condition is occurred after the 16 second. Then for the case 8, which is temporary bolt three-phase fault at bus 11. So this is the figure. The fault is made by making a short circuit at the area by tapping each line and ground at a specific time. The fault that is created is by the value 0.001 ohm at the 14 and 16 second. So for fault at bus 11, the graph you get for the tapping at the 14 second, the most stable condition is from 8 until 14 second. The unstable condition is occurred after the 14 second and above. Then the graph when we tap the fault at 16 second, the most stable condition we get is from 10 until 16 second. Then the unstable condition is occurred after the 16 second. Alright, that's all from me. Thank you.
So it will happen because due to voltage instability. So in conclusion, at the end of this experiment, we are able to achieve all the objectives that has been given. We know and able how to model the test system model of power system using MATLAB Simulink. From this experiment, we can analyze the dynamic response of the system by following a disturbance that has been stated. All of group members brainstorm the idea to solve complex power system problems in a group within a limited amount of times. So that's all from us. Thank you for spending your time.